Welcome to the Learning Pines YouTube. We hope this video helps.
You begin by computing the characteristic polynomial det, a minus lambda I, and solving for eigenvalues. This gives you the targets for diagonalization. Once you have each eigenvalue, compute its eigenspace by solving a minus lambda I x equals 0 to produce eigenvectors. Make sure the sum of geometric multiplicities equals n. If it does not, you cannot diagonalize. As you extract eigenvectors, normalize or scale for convenience, because later you'll assemble them into the modal matrix. Now assemble the eigenvectors as columns of matrix P in the same order you will place eigenvalues on D's diagonal. Compute D as the diagonal matrix, whose entries are the eigenvalues corresponding to each column of P. Next, check that P is invertible by computing det P or rank. Invertibility is essential because it equals PD P minus 1. Once you have P and D, compute P minus 1 a P to confirm you obtain D. Small arithmetic mistakes here are the most common source of errors. Finish by computing P minus 1 and explicitly forming P minus 1 a P. You should recover D exactly. If you encounter repeated eigenvalues, make sure you found enough independent eigenvectors. Geometric multiplicity must match algebraic multiplicity. If it doesn't, the matrix is not diagonalizable, and you should instead compute its Jordan canonical form. One troubleshooting tip: when numeric rounding causes near dependence, use symbolic arithmetic or rational approximations to check linear independence rather than relying on floating point rank.
Thanks for watching. Consider subscribing if we helped you.